Welcome everybody to the 5th of November day for the world scientists' warning of climate emergency. Today is the actual anniversary of when the world scientists' warning of a climate emergency was issued, as well as being the one-year pre-anniversary of COP26. And we're all here because we want to see a lot of action on the climate crisis now, on the way to COP26, and very importantly at COP26. Well, today is our short-lived pollutants day. We selected all of the 6 stressors from the world scientists' climate emergency warning, and we're covering short-lived pollutants today. And as a start, I want to read out the chapter from the world scientists' warning of a climate emergency on short-lived pollutants. We need to promptly reduce the emissions of short-lived climate pollutants, including methane, black carbon or soot, and hydrofluorocarbons or HFCs. To do this could slow climate feedback loops and potentially reduce the short-term warming trend by more than 50% over the next few decades, while saving millions of lives and increasing crop yields due to reduced air pollution. The 2016 Kigali Amendment to phase down HFCs is welcomed. It's particularly topical today, as you may well have seen the research that came out just a week ago from the Russian research ship academic Keldysh that was in the Arctic and identified more methane release, and the suggestion was that that may be the start of the tipping point. You'll also probably be aware that an Antarctic iceberg the size of Norfolk, 150 kilometers long and 48 kilometers wide, is traveling on a trajectory towards the British Atlantic island of South Georgia. With all that being so topical, it's an absolute welcome to have Professor Peter Wadhams here. Peter is, of course, one of those who's been with Scientists' Warning, in fact, the longest, was associated with Stuart Scott with a lot of the work that he was doing a number of years ago, and is on the core team of Scientists' Warning Europe now. Peter is currently visiting professor at the Turin University in Italy, doing teaching and research on climate change. He's also Professor Emeritus at Cambridge University and was the Professor of Ocean Physics and head of the Polar Ocean Physics Group in the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. While at college, Peter was an assistant on the Hudson 70 expedition, an 11-month Canadian cruise which accomplished the first circumnavigation of the Americas. He did his PhD at the Scott Polar Research Institute at the University of Cambridge on the effect of sea ice cover on ocean surface waves. Peter has also served as a director of the Scott Polar Institute in the University of Cambridge. So Peter has 50 years experience in Arctic ice, is an explorer as well as a scientist. So we hand over to him now for a discussion of methane and short-lived pollutants. Thank you, Peter.
Well, thank you very much, Ed, and it's a real pleasure to be able to talk today. And what I'm going to talk about is of all the short-lived climate pollutants, I'm going to talk purely about methane because it's the most serious pollutant apart from carbon dioxide in the atmosphere. And the story of methane really is a story of a very serious, definite threat to our future existence on this planet. And that's why, hence the title of this talk. So I'm going to talk mainly about that threat, and the threat derives from methane being emitted from underwater in the Arctic, in the shallow Arctic seas, and that implies a collision between 2 changes which are going on in the world. One is that sea ice is disappearing in the Arctic, and this is allowing the sediments under the Arctic seas to be released and produce methane. And then the other is, of course, what methane itself does when it gets out into the atmosphere. So the start of the story really is in why is there a lot less sea ice than there was in the past? all of the changes that are happening now depend on the fact that the sea ice is disappearing and allowing the continental shelves of the Arctic to warm up. So I'll start off, assuming I can get hold of my talk here. Here we go. Talking about the question of why is the ice disappearing. So, okay. Right. Well, if you want to read more about this, I of course recommend my own book, which is called A Farewell to Ice, and is available as a very, very cheap Penguin book. And this explains all the things that I'm talking about and more. Seem to be having some trouble moving on my slides.
Peter, do you need to click in the middle of the screen to move on to the next slide?
Okay, I see, yeah. Right, good.
Okay, cool, sorted.
Well, anyway, my book is available in many languages besides English, and I know some of my viewers today are from Italy because that's where I'm talking from, and the Italian version of this book is called Addio ai ghiacci. The thing that's different about it is it has a very peculiar animal on the cover that seems to me to be a giant mouse, but the publishers assure me that it's a polar bear who's distraught because there's no sea ice around and he hasn't got anywhere where he can go to get food. Okay, so we start off with where did the sea ice come from and why do we not have any now, or very little now? Well, when the Earth, this is a kind of potted history of the planet, going back in a number of scaled sheets going back to 500 million years ago. And we can see that 500 million years ago, the Earth was a lot warmer than it is now. The line halfway down this graph shows present average temperatures, and so the Earth of 500 million years back was a much warmer planet than it is now, and then it gradually cooled off until around about 1,000 years ago, a million years ago, it cooled off enough, which is the second from the right panel, to actually start into some kind of oscillating pattern of cold and hot that was related to small astronomical changes in the Earth's orbit and the angle of the Earth's orbit to the orientation of the Earth. And so this gave us what we now think of as the ice ages that go back forever, but only go back actually about 1 million years. And here we had, at this slow rate, we had an oscillation between warm temperatures, is what we have today, and cold, much colder temperatures, which were ice ages. And the very last panel shows what's happened since the end of the last ice age. We emerged about 20,000 years ago. We started to warm up, and the temperature reached a warm level, which it has remained at for the last 12,000 years. And we're due to head for another ice age soon, according to the astronomical theory. But the problem is we may not actually reach that ice age because of all the extra warming we've been inducing in the planet through the carbon dioxide which we've been adding. So that's the long-term history of the planet. And now we look closer in and we look at the last 400,000 years, which encompass 3 to 4 ice ages. Each ice age seems to take 100,000 years, in which first of all, the planet cools off quite slowly towards the very cold ice age conditions, and then it jerks itself out of that very quickly. So you have a sawtooth pattern of temperatures on the planet, in which we go into an ice age slowly, gradually. Glaciers accumulate snow and ice, and then when the orbit of the planet changes very slightly, we get a warming, and the warming is enough to melt that ice quite quickly, so we jump back into warmer conditions. So the last jump of 15,000 years ago brought us to our present interglacial. So that the top picture here shows what happened to the carbon dioxide, or the bottom one actually shows the carbon dioxide. The top one shows the temperature. This comes from ice cores drilled in the Antarctic. Now the carbon dioxide has gone through a cycle where it oscillates between about 280 parts per million in a warm period and 180 in an ice age. And amazingly, all the ice ages we've been able to study, that oscillation, those two endpoints, 180 and 280, have been the same. We don't know why, but they have been, until our present situation, where we came up to 280 15,000 years ago. We stayed at 280 right until 150 years ago, which is when we invented global warming by starting to mine coal and burn coal, and then eventually burn oil as well. So we brought on a greater warming than the Earth was subject to naturally, and we brought on a greater CO2 level. So the little red line on the right shows how much of an increase we've produced simply by our own emissions of carbon dioxide from burning coal and oil. And it's a big difference that we've made. We've taken the planet way beyond any natural variation that it's had between ice ages and non-ice ages. Now we come on to the more recent past, and this is some data on global temperatures over the last 1,000 years. And this is from a variety of sources. But if we look at the lower part, Northern Hemisphere history, we find that 1,000 years ago, the Earth was a bit warmer than it is now. We were at our height of the interglacial, and we had slightly warmer conditions. So, for instance, the Vikings were able to colonize Greenland, and you could grow enough hay and grass to keep sheep. Then suddenly, we went from that very gentle cooling that we see, which was basically the Earth heading slowly towards its next ice age. But suddenly that stopped in the 19th century, and the temperature started rising very rapidly. This has happened ever since. The top graph shows an expansion of the last 100 years. But basically, the rate of change is quite different from what it was when natural conditions prevailed, which was ever since the Ice Age right until 1850. So it is remarkable how the Earth the Earth's temperature has been really subject purely to natural oscillations and natural forces right up until the middle 19th century, when we started to interfere with it by mining coal and burning it. So we've made all the difference that we've experienced since. So it's not, I mean, climate change deniers, which a timely, I suppose, thing is the US election of the last few days, where when Republican senators were questioned about climate change, they had a sort of a hymn book where they say what they'd been ordered to say by Trump. And what they were ordered to say was, the jury's out on whether climate change is due to man or not. Because the jury hasn't been out at all. It's definitely due to man. But that's what they have to say for political reasons. So the jury's not out. What actually has happened is that we have produced a massive change in global temperatures and global CO2 levels by burning coal and then burning oil and having an environment and a civilization based on fossil fuels. At the same time because the temperature was going up, this was being caused by gases, greenhouse gases in the atmosphere that we were putting out, primarily carbon dioxide, but not entirely carbon dioxide. Here we see carbon dioxide content in the atmosphere showing the huge rapid increase that happened in the 19th century and has continued ever since. But we see that the climate change happened to methane and nitrous oxide, two other components of the atmosphere which are affected by mankind's activities, methane especially. So we've been adding not only a long-lived gas. I mean, carbon dioxide counts as a long-lived climate gas because once you put it into the atmosphere, it stays in the atmosphere for thousands of years. The processes that get rid of it are very, very slow. Whereas methane, nitrous oxide, gases like that are called short-lived gases because there's processes that go on in the atmosphere to get rid of them. Methane is oxidized in the atmosphere, and a molecule of methane released from natural gas or from underwater only stays in the atmosphere for 10 years before it's oxidized. So these are called short-lived gases. There are, as said, there are even more short-lived pollutants like black carbon, which is deposited from the emission from burning of dirty fuels. So that's the recent past. So when we translate the recent past and the present to different parts of the world, we find that the Arctic is warming up much faster than the average. Instead of the whole world on average has warmed up about 1 degree since the Industrial Revolution, but the Arctic has warmed up by much more than that, by more like 3 degrees, and it's warming up even faster now. So if we look at warming rates versus latitude, we find this huge amplification in the Arctic. And that's obviously going to have an effect. Dealing with a cold part of the world, the Arctic, and you're dealing with increased warming rates, then the first thing that's going to happen is a change of state, and all of this frozen stuff is going to turn back into water. So the frozen stuff, really, there are two kinds of ice in the Arctic. One is solid, pure ice on ice sheets. That's the ice found on the Greenland ice sheet, 2 miles thick. And the other is the sea ice, which grows from the freezing of seawater. So if we look at the sea ice now, which is the most rapidly varying substance, we find that as far as we know, it started to retreat most rapidly from about 1950 onwards. So the bottom graph here shows sea ice extent since in different seasons of the year since the 1900, and we find 1950 was really the start point of a big retreat of sea ice in the summer, that's the bottom graph, and the sea ice in other seasons, that's the other colours, has also been retreating but slower, so it didn't notice so much at first, that people weren't aware that sea ice was retreating at all times of year, but because the effect in summer overwhelmed the rest. So what does that do? Well, the first thing is that instead of the whole of the Arctic being ice covered in summer as well as winter, the summer ice started to visibly retreat and started to leave big areas of open water in the Arctic basin. So the bottom right shows the first year in which the retreat was so visible that really it was distinctly different from the original situation. In the past, the summer ice average position was the little pink line, and we could see that nearly all of the Arctic was still ice covered. And then in 2005, it retreated more. In 2007, that's the bigger picture, it retreated much more. So we already had, in summer, a big open sea in the Arctic Ocean. And that's been the situation ever since. We've had a lot of retreat going on in summer, leaving big areas of open water around the edges of the Arctic. Now, the important thing from a methane point of view is that these areas lie over shallow water. The Arctic Ocean is a very unusual ocean. It's deep like other oceans in the centre, about 4,000 to 5,000 metres, but it has very wide continental shelves that occupy about a third of the area. And those continental shelves are really shallow, the 50 to 100 metres water depth, mainly because of huge amounts of sediment brought down into the Arctic Ocean from large Arctic rivers. So we have this unusual situation of an ocean which is not like other oceans, because instead of being deep all over, it's only deep in the middle, and with very large shallow shelves around the outside. So this is what it started to look like from 2007, and it's looked like that ever since. And in fact, it's retreating even more now. But this shows, for instance, a more recent year. That's the 2012, where the white area is the remaining ice. The yellow was the 2007 record low, and then the black was the previous average. So we see the way in which the summer ice is closing in, but the remaining ice is mostly in the centre of the Arctic Ocean, and the part that really has retreated most has been from the shelves, the edges. And we see now around the Beaufort Sea and the seas north of Siberia, very large areas of open water in summer, which remain open for about 3 months. So this just shows how fast this change has been and how poorly scientists understand it, because the red line shows the decline in sea ice extent in summer, which means that we can see that it's going to be disappearing completely pretty soon. And the black lines show the results of various computer predictions of what the sea ice extent should be in summer. And the thick black line is the average of all the climate models that people have used. And we see how bad they are, that they're still predicting that there'll be lots of sea ice around by the end of the century. So we can see there's a disconnect between climate models for sea ice, which are no good at all, basically, and reality, which is showing a more rapid retreat. The models, which we see here, are all the models used by Intergovernmental Panel on Climate Change for its climate predictions. So already this raises a warning about how much can we trust the Intergovernmental Panel on Climate Change, which supposedly gives us due warning of changes and what we can do about them, it's not picking up on sea ice retreat properly at all. And that makes you wonder if it's picking up on everything else properly as well. Anyway, if we consider this retreat, and we also consider the fact that the ice is getting thinner all the time, because as it melts, and we've been measuring the thickness by going up to the Arctic every so often in submarines and measuring the thickness with sonar. If you combine the thickness and the area together, you get a volume, and we can see that the volume really has been seriously diminishing. So this is since the late 1970s until, and it's continued actually in the last few years, we see a decrease of more than 75% in the volume of sea ice in the Arctic during the summer. And so when we look at the Arctic in summer now, we're only seeing a quarter as much ice as was there as recently as 1980. This is shown most graphically in this famous way of representing it, which is called the Arctic death spiral. And it shows the volume of sea ice in different years, going from 1979 round to the present, and for each month of the year. So September, which is the month of greatest retreat, is the black line here. And we can see that if sea ice did not retreat, you'd have a set of concentric circles. But the fact that it is retreating means we're spiraling in towards the center. And when it reaches the center, of course, it means there's no sea ice left. And the black line is going to reach the center first. So the September sea ice will disappear first, and then the other months of the year will follow a few years after that, or a few decades after that. This shows just the August sea ice extent and how that's diminished. Now, what does that mean for us if we're out there looking at sea ice, looking for sea ice? Well, the first thing is there's these big areas of open water around the coasts over the continental shelves. And then where there is some ice left, it's nowhere near as thick as it used to be. This is ice in the 1970s, and this was called multi-year ice. It's ice which stayed around in the Arctic year after year, got thicker and thicker, and got very, very rugged. But when we look now, this is what we see. This is in that same location, north of Alaska, and the ice that I'm showing here disappeared completely a week later. It's really thin. You wouldn't want to walk on that, you'd fall through. So this is what we see now in the area where we used to have very thick, rugged ice. In fact, you don't need an icebreaker to get through this ice, although this is in fact a US Coast Guard icebreaker. And this is what it looks like. First year ice, this is my screenshot here is of typical Arctic ice today. Much thinner. Some of this ice you could fall through. This is a refrozen lead. It's only about 1 meter thick, and it grows and disappears in the same year. So the old multi-year ice, which used to prevail in the Arctic, that's the red area here, has vanished during the last decade, the last 2 decades, leaving only either open water or first-year ice. So what does that does a lot of things to the world. Now, one I'm going to talk most about is number 5 here, which is that there's a direct and immediate threat to our livability of the planet from methane, which is being released now from under the ice, or from under where the ice used to be. But the retreating ice has done other things as well. it's caused the thinning and retreat of sea ice is giving you more open water, and that gives us a decrease in the planetary albedo. Albedo is the fraction of the incoming solar radiation that's reflected straight out into space. That's gone down, and so the Earth is retaining more of the radiation that comes down from space, and that's increasing the rate of global warming. At the same time, the warming has caused snow to retreat. So the Arctic snow line is gone back from where it used to be, and we find a lot of areas we familiarly think of as snow-covered are no longer snow-covered. And that as well decreases the albedo, because the retreat of snow also replaces white substances by dark substances. The warming also is causing the Greenland ice sheet to retreat, to melt more rapidly, and the melting of the ice sheet puts a lot of fresh water into the ocean. And the extra fresh water going into the ocean gives you a greatly enhanced rate of global sea level rise, more than we were getting in the past when global sea level rise was simply due to ocean water warming. Then we have the methane problem, and we have further problems due to the circulation of the currents in the Atlantic changing and us getting extreme weather events. That's really for another lecture. So the albedo effect is that here's where the summer ice used to be, the limits of summer ice before it really started to retreat. Here's the limits now, and the difference is the blue area. So that blue area is now ice that's disappeared in summer, leaving open water, which has a very low albedo, absorbs nearly all the radiation falling on it, warming the planet. But the old ice covered the Arctic, and we got therefore less warming. Now that big increase in melt in summer is causing, first of all, an increase in warming of the water and the air temperature around the shelves of the Arctic. This red shows the anomaly we have in November, when normally the sea is freezing again. Instead, nowadays, it doesn't really freeze in November. So, and this is the snowline retreat. The brown is snow that now has disappeared from places we used to think of as snow-covered always, like Alaska and Siberia. There's the anomaly. This shows the retreat of the Greenland ice sheet. As the ice in the Arctic Ocean disappears in summer, then it causes a warming of the ice sheet. So Greenland ice sheet, which normally is frozen year-round, is now not frozen year-round. In the summer, we now have a melt, and the blue shows what happened, for instance, in 2012, where the ice sheet, which in previous years or earlier the same year would remain frozen over most of its area because it's 10,000 feet above sea level. But now the amount of warming is so great that nearly the whole Greenland ice sheet shows melt in summer, and the mass of ice in Greenland is diminishing very fast. This is shown by a satellite which responds to the mass of ice underneath it. So it's a mass measuring device, and shows that the mass of sea ice, a mass of land ice in Greenland is going down very fast, which is causing us to continually uprate our estimates of how much sea level rise we're going to have during the rest of this century. IPCC in 2007 was giving this very remarkably low rise. That's because it's an organisation which specializes in complacency. But the measurements that have been taken by glaciologists of the retreat of Greenland ice is giving us more and more rapid sea level rise. So now we're going to be getting at least 1 meter of sea level rise this century. And I'll leave that out and go on to talk about methane, which is what the talk is mainly about. Firstly, the threat exists. This summarizes what the threat is the fact that it's over these shallow shelves, which only have a water depth of 50 to 100 meters, that you get the melting of all the sea ice in summer. And that means that the open water can warm up because you're getting a lot of solar radiation in summer. You get 24 hours of daylight per day. The radiation warms the water over the shelves, and instead of that warming just extending to the top surface of the water, the water depth is so shallow that the heating goes on down and extends to the bottom of the shelf water, and that warms the seabed. So the seabed is warming, and in doing so, it makes it capable of releasing what's down there, which is normally frozen. And what's down there is a lot of sediment containing methane. So this is the threat, is that the melting of the seabed, or thawing of the seabed, due to the warming of the coastal seas by when the sea ice disappears, is going to be giving us some very, very much rapidly increased emissions, in this case of gaseous methane. So here we are with the bathymetry of the Arctic. We see the light blue is the continental shelves, only 100 meters deep or less, and they go all the way around from the Bering Strait via these named seas, the Siberian Sea, Laptev Sea, Kara Sea, and Barents Sea, which are really all one joined up shelf. And then the dark blue is the deep water in the middle. So when the sea ice retreats in summer and just leaves a sea ice covered area in the middle, all these shelf seas become ice free. And when we look at those shelf seas in summer and sense the temperatures at the surface, we find they've warmed up a lot. This here, for instance, is the August sea surface temperature in the Arctic in 2007. And we see that the blue is where the ice edge is. This area is therefore ice-free, and it's warmed up now so that in this middle area, part of it, you're getting temperatures above 5 degrees C. Now that's got worse since then. In fact, when I sailed up this way in that icebreaker that I showed, we actually had temperatures of 17 degrees in north of Bering Strait and 11 degrees out in the Arctic Ocean. Those are temperatures like you get in the North Sea in summer when people go swimming. So this is not typically Arctic conditions anymore. When we look at the temperatures down deep in the ocean, not deep because it's not deep, but down near the bottom, we find that temperatures are still well above freezing point. This is moorings that were placed on the seabed, and we find temperatures well above zero over most of the depth of the water. So we've got warm water. So what does it do? Well, when we look below the warm water, we find a layer, first of all, of permafrost, like you have on land. That's permanently frozen ground. And underneath that permafrost, we've got a couple of 100 meters of sediment, and that sediment is absolutely sodden, so to speak, with methane gas. But the methane is reacted with the sediment to produce a kind of a substance called methane hydrate, which is partly ice but the ice is a cage-like structure that contains methane molecules. So it looks white, it looks like ice. Here's some that's been dredged up, and you think this is ice, but in fact you put a match to this, it burns. It's extraordinary stuff. It's ice which burns, and it's basically methane just contained within the structure of ice. Now this is called methane hydrates, and methane hydrates are found in sediments all over, not only all over the Arctic, but all over the world. And it's just that in the Arctic, you can get at them because the water's so shallow. So the left-hand picture here shows extent of methane hydrates over the Arctic Ocean. We see this big area of blue on the East Siberian Arctic Shelf, ESAS, but there's blue everywhere. But the trouble is, it doesn't matter if there's hydrates in the deep ocean. They remain stable and stay down there. But the hydrates that are in the shallow water become unstable, and that's when they release methane gas. So on the right-hand side, we see the water depth. And so we can see the East Siberian Shelf is the only shelf area in the Arctic that combines very low water depth on the right with high concentrations of sediment, hydrates in sediment. It is fairly complex structure. This actually shows in detail some of the geological structures in the East Siberian Shelf. But when you look in general, if you look along this red line here, we find along here, this should be kilometers, by the way, the light brown here is methane-laden sediments. That's the light brown. These are deeper sediments which don't have any methane. But the methane covered layer is about 2 kilometers thick. So we've got 2,000 meters of sediment, which is absolutely high concentration of methane. And this is what happens, that the methane is held in the sediment by the fact that there's this layer of permafrost above it. But as the seabed warms up because of the global warming and the warming of the ocean, that permafrost melts and you're left with kind of naked sediment in the form of the hydrates. And naked hydrates are not stable at this water depth. They decompose into methane gas. And here we see places where methane gas has been released, or is being released. This is a sonar image taken from a ship looking sideways at the East Siberian Shelf. And this is water depth. So the water depth here is only 70 meters. This is the permafrost layer at the bottom. And this is where methane has broken through, is rising in big plumes to the surface. So it is a very dense collection of plumes. If you sailed your ship across that, you'd have to be very careful not to have any naked flames, otherwise your ship might blow up. This is looking from below at these methane bubbles coming up. This is a photograph taken from an underwater vehicle. This shows the bubbles rising towards the surface. And this shows a case where there's some ice at the surface, which is flattening the bubbles against the bottom of the ice. So while they wait to find a way through the ice, get into the atmosphere. So this is the truly frightening thing of huge amounts of methane release from the seabed coming up to the sea surface, being released into the atmosphere. We can tell where this is happening because if we look at the right-hand picture, the pink here is places where the seabed is fairly stable. So where it's the melting of the permafrost that's allowing the methane to come out. The yellow here is where the actual sediment on the seabed is broken up by the presence of geological imperfections in the seabed called talics. That's an Inuit word meaning a geological imperfection. And the talics provide conduits by which the methane can come up. So the methane plumes are even more common in the yellow areas than in the pink areas. This shows the Laptev and East Siberian seas. And some of that methane, of course, dissolves in the water. Now, scientists have been very complacent, and IPCC, in fact, I think has been intolerably complacent about this phenomenon, because what they say is, oh, well, methane released from the seabed just dissolves in the ocean and doesn't reach the surface. Now, that's actually wrong. It's true if the water depth is great, if the water depth is more than 200 or 300 meters, but it's not true if the water depth is only 50 or 60 meters, because the methane gas rises quickly, comes out of the surface of the water into the atmosphere. It doesn't have time to dissolve. If the water depth is great, the methane dissolves. So a lot of scientists who have never been to the Arctic imagine that the methane dissolves in the water, so we don't have anything to worry about. They're just not aware that the water depth is very shallow. So this is where we do have methane. Some methane does dissolve, of course, and this shows methane levels in the water in the Arctic seas. The different colours here show the various seas, Kara Sea, Laptev Sea, but all measured up before 2012. But the grey here, this huge peak, is measured in 2018. The last two cruises done by Russian scientists called Natalia Shakova and Igor Semiletov. These are the two leading Russian scientists who worked up there most. And they find a big increase in the dissolved methane as well as the methane coming out. So this methane hydrates, as I said, everywhere in the world ocean. The blue blobs show where you can find it in coastal regions, but these are, again, all deep water regions, whereas this region along the East Siberian shelf is shallow. We know that something's been going on in the last few years, because if we look at the amount of methane in the atmosphere, it grows steadily, and then it reached a peak in about the year 2000, or stayed at a same level. This was partly because a certain amount of care was being taken. A lot of the methane that's emitted to the atmosphere is released from pipelines, gas pipelines, and initially people didn't care much about methane leaks from pipelines, and then when gas got to be more expensive, they took more care, and now we have less methane being accidentally released. So the methane stayed at a fairly constant level, and people felt fine, we've got methane under control. But then around about the year 2007, detectors started to show an increase. The methane was starting to go up, and it's been going up ever since, and with an accelerated way. This is a methane measuring instrument in the Arctic, and ALERT, which is on the north coast of Ellesmere Island in Canada. And this shows the seasonal variation in methane, the fact that it stayed fairly stable, and now the fact that it's going up fast. So this is what's happening wherever we look now. Methane is increasing. And we think that this is largely due to methane being released from the Arctic underwater. This shows methane as measured from a satellite. Leonid Yurganov is the world's expert on measuring methane concentrations from different kinds of satellite. And this shows a change over just a 3-year period between the amount of methane in the atmosphere over the Northern Hemisphere on the left in 2008 and on the right in 2011. And there's a significant increase over those 3 years, and we see from the colours. We see it also from his map of methane distribution in the atmosphere over the whole world. And we see that there's a higher level of methane in the northern hemisphere than in the southern hemisphere. Now, methane mixes very quickly in the atmosphere. You release methane somewhere and it spreads quickly all around the world. But here, the fact that there remains a higher level in the northern hemisphere means there's something replenishing the northern hemisphere more rapidly than the southern hemisphere. And we suspect that's the Arctic. And again, we can see an even higher level over the Siberian Arctic. So what could that do? Well, at the moment, the release is enough to make a detectable difference to the methane concentration on the planet. But what scientists fear, especially the Russian scientists who know most about this area, is that the whole of this protective layer of permafrost will thaw all in one go, exposing the entire shelf of the Siberian Sea and other seas nearby, the Laptev Sea, Kara Sea, and the Sea of Okhotsk, releasing all the methane. The hydrates basically become naked, they break up, the methane is released, and in one go, we could get a huge burst of methane. This is the fear of the methane gun, the methane outbreak. Now, a Russian scientist who's estimated how much could escape in one go has estimated 50 gigatons as the initial release from such a burst. 50 gigatons is 50 billion tons. And I did an analysis with 2 colleagues of what that would do to global warming. Now, this is not a very good picture because it's got the background in, but the blue line here shows the predictions of how warming is going to affect the planet over the next few decades. We'll get warming continuing, of course, because we're not doing very much about it. But the red shows what would happen if we added a methane burst. We'd be getting an extra 0.6 of a degree emitted more or less immediately, a sudden step in global temperatures of 0.6 of a degree. Now, this is not good news because the entire amount of warming that's happened since the 19th century has only been 1 degree over the planet as a whole. And here we are saying, well, this methane burst would add 0.6 instantly, and by instantly, it's within a few months or weeks. We don't know how instant is, but it's very instant. And that a step change like that is something we've never experienced on this planet. We've had warm winters, warm summers, unusual heat waves, but to have a permanent step in our temperatures of 0.6 of a degree is something unprecedented. And it would just be the start, because that 0.6 degrees would be followed by more as more of the sediments melted. We used a model that was used in the Stern Review of Climate Change, which estimates economic costs. And the economic costs turn out to be at least £1 trillion a year. That's the damage done by this big input of methane into the world's climate system. Now, when I first published this curve, people were outraged and thought, £1 trillion, that's an unspeakable amount. Nothing could be as that great. But then, of course, since the COVID virus, we're now used to talking in trillions. Trillions of what it costs to have a virus acting for a few months in a normal sized country. So trillions are now not as frightening as they used to be, but trillions are what we're going to have to pay out if we have a methane outbreak. And the estimate is that over a century, there'd be $60 trillion would be what the methane outbreak will cost us. The other thing would be methane will be a bigger contributor to global warming. At the moment, carbon dioxide is the biggest contributor, and methane follows along behind at about a third of that level. And then there's various other components. But if a burst happened, methane will become a much bigger contributor to global warming. It would start to rival carbon dioxide. So what can we do about it? Well, we know, but the problem is we don't know. And we know how we can get rid of carbon dioxide. We have to spend a lot of money, but we can take carbon dioxide out of the atmosphere. It's not just a matter of reducing emissions. We can actually chemically remove CO2 from the atmosphere if we spend enough money and have enough plants to do it. But that doesn't apply to methane. So people have thought of different ways of dealing with it, but we need to really think about this urgently, because this big burst could happen any time. And the estimates are it will happen within the next few years because of the way in which the protective permafrost layer on the seabed is disappearing. So one way that's been proposed, there's very few ways that anybody has proposed. So this is an area of active research. One way has been marine cloud brightening. Now, here we have a marine cloud brightening device developed by a scientist in Edinburgh, Stephen Salter. And what that consists of is firing or blasting up seawater to a high level by running up the inside of masts on drone ships. And the seawater comes out the top through a fine nozzle as very finely divided particles, which then move into the low cloud, which you have over most of the world ocean, and it brightens the clouds. This is something that would be very popular in Britain, where we've got miserable grey clouds everywhere. This brightens the clouds, makes them whiter, and they reflect more radiation, and that cools the planet. So if you have a lot of these drone ships all injecting finely divided seawater into clouds, it can reduce the temperature of the planet. And by reducing the temperature of the planet, especially if we aim this at the polar regions, we can have these drones sitting around near the edge of the ice in the Arctic. Then it will cool the Arctic and mean that the seawater around the edges of the Arctic stops being warm, starts being cold again, and that means that the permafrost stops melting, and so the methane stops coming out. So it's a way of sealing up the methane again by cooling the Arctic regions by this marine cloud brightening method. This was invented in Britain. The chap who invented it is a brilliant engineer, Stephen Salter. He invented the first wave power devices, but there's no sign that our government is going to be spending any money on this, although it's the most promising way of dealing with this particular form of climate threat. And Britain leads the world in that, but of course, they're letting that all go to waste.
Peter, just to let you know, we actually have sort of reached full time, although if people are happy to stay, we can extend by half an hour if you're happy, but we're going to try and include some questions as well.
Okay, I'll finish. I've only got about 2 minutes to go, so I'll finish quickly. And the quick finish is to say ways. That's why it's a short finish, because we don't know really how to get rid of this methane. Marine cloud brightening is promising. We think that would work. Direct air capture reduces the temperature of the whole planet by getting rid of CO2. That's not doing anything specific to methane. And the other method is, this just shows the tracks followed by the ships that have been working up there. That's the Russian ships. And I'm going to refrain, through lack of time, for talking about the other source of methane, which is methane on land. And I'll just show this picture because it shows one of my favorite places on the planet, Dead Horse, Alaska. And this is where most of the northern hemisphere of the Earth is covered with permafrost. And another source of methane is the fact that permafrost on land, that's frozen ground, is itself slowly melting. And this shows the warming of a permafrost layer in Alaska over the last few years. So if we escape this terrible methane outbreak that everybody's frightened of, we're still going to have an increase in methane, a slower one, but more long-lasting, because permafrost on land is also melting and slowly melting away, while the methane under the sea is likely to disappear suddenly. That will be the dramatic threat, while the longer-lived threat is the slower melt of methane, slow emission of methane from permafrost on land. The reason I mention that Dead Horse is it's a very interestingly hideous place on the north coast of Alaska. It's got an airport, which is also called Prudhoe Bay Airport. It's in Prudhoe Bay where oil development has happened. And its population is the only town in America listed as having a population of 1. And the one person is the person who runs the airport. And I have good reason to be grateful to this man because a few years ago, I was in an accident on board a submarine, which nearly sank. And all the surviving crew, we were flown in to Alaska by a helicopter and left to our own devices. We weren't supposed to land. Our ship was a Royal Navy ship supposed to go back to England, but instead we all got evacuated to Alaska, and I had the problem of how do I get back? So I went along to the airport and saw this one person, population 1, and he went to his computer and immediately found me a set of flights that got me to London from the most remote spot in Alaska within a day, a set of flights that flew me to Fairbanks and Seattle and then to London. I thought that was just a brilliant achievement for a guy who sits there all by himself in this deserted airport, which only deals with flights for oil companies. I thought that was brilliant, and so I always think fondly of Dead Horse, and this is why I mention it, because of these measurements that were done of permafrost there. So this is the problem then, that we've got a direct threat of a large outbreak of methane into the atmosphere from the Arctic Ocean seabed, because the water is shallow and it's now exposed to the atmosphere in summer because the sea ice is disappearing. That produces a direct specific threat which could do a terrible amount of damage by producing a big step change in global warming. So we've got to try to find a way to get rid of it. We don't know a good way. And if we can't get rid of it, we'll have to cope, even if it doesn't happen. We'll have a slower release from permafrost on land, which is just as harmful in the long run. So at the moment, we're doing some work, a group in England and internationally, in fact, is working with a technique called iron salt aerosol, where you're blowing a powdered iron in the form of ferric chloride over the sea surface, where it is supposed to react with methane and get rid of the methane. So there's field tests still to be done on this, but there's a potential solution in the form of this iron salt aerosol, but we don't know whether it will actually work or not until these first experiments have been done. So that's the situation for the methane threat, and I think you should be worried about the methane threat, despite the fact that the Intergovernmental Panel on Climate Change is keeping very quiet about it. Thank you.
Great, thank you, Peter. If you might turn off your screen sharing now, possibly as well, please. And we'll go straight on some questions. Seeing what somebody had already written and your last comment, I think it's worth asking, why do you think the IPCC is not giving the same picture as you are? And what should be being done about that?
Well, firstly, there's a lack of knowledge, because the people who've worked intensively in that part of the world are really one group only, this Russian group, because in the East Siberian Sea, where the biggest effects are happening, this is Russian territorial waters or Russian economic zone, and nobody else is allowed to work there. So you're dependent on research cruises into the area by the Russians, and it's just this one group of Russians that can go there. Now, they publish all their results in very prestigious journals, so there's no excuse for international scientists not to be aware of those results, but they often are, because of the parochial nature of a lot of scientists. And most scientists then who are interested in methane think only about methane in deep water, so they're not even aware that methane comes out into the atmosphere, despite the fact that there are very dramatic photographs and film of this happening. As you probably saw if you've been reading The Guardian, that the most recent Russian expedition, which has just returned, has got some very dramatic film of methane plumes coming out of the ice, of the ocean. Now, every time you go up there, you get these dramatic pictures. So really, there's no excuse for scientists to be unaware of this. But the Intergovernmental Panel on Climate Change, not just with methane, but with other things, has a tendency to underplay the rate of warming. You would think that they don't, because their most recent report on how do we keep global warming to be below 1.5 degrees is saying, well, we've got to do some drastic things. But as a whole, if you look at the assessments that they've done over the years, they always seem to underplay the amount of warming that's going to happen, and therefore the urgency of dealing with it. This is for political reasons, I think, partly because it's an intergovernmental panel. It's not an international science panel. The government representatives have a say in what comes out in its reports, and it's always in their interests to underplay the magnitude of the effects, so that it looks as if you have more time to deal with them, so you don't have to treat them as urgently as really you should. So and this is being kind of revealed now in quite a lot of articles about IPCC and its tendency to underplay warming, because it's quite dangerous. I mean, if you're an international organisation and you're supposed to give a correct warning about a change that's happening, you shouldn't be underplaying it. You should be, the precautionary principle says you should be making people aware of a danger rather than concealing it from people.
Yes, and their summaries for policymakers are showing what the 65 or 75% likelihood of something is, as opposed to the totally catastrophic 2% or 5%, which policymakers should really know about as well.
Yes, exactly. They don't give the range of possibilities.
Okay, we've got more of a comment here, but I'll read it out and then maybe you'd like to make a quick comment on it. From Peter Dines: if we reduce the aerosols, we will also spike the temperatures due to a loss of masking effect. Solar radiation management is needed urgently to mitigate 2D solutions, much more efficient and scalable than 3D. Any comments?
Yes, I'd agree with that to some extent. First of all, the initial effect of reducing methane is that if you reduce the amount of aerosol being produced, then you need the initial effect is warming, but it's only an initial effect. I think the other part of the question concerned concerned marine cloud brightening. I mean, yeah, I agree that marine cloud brightening, for instance, is in this case a way of getting rid of cooling the climate locally, so that you reduce the methane content or the methane emissions. But in the long run, it can cool the climate locally or regionally, but it doesn't do anything about carbon dioxide content. So it doesn't deal with a very key problem, which is acidification of the oceans due to additional carbon dioxide dissolving.
And do you think would give us a false sense of security? So it allows us to keep polluting for another period of time while that's protecting us?
Well, that's again been one of the reasons why, I think it's one of the reasons why Greenpeace and even IPCC are not recommending marine cloud brightening, are not recommending geoengineering in general. That's trying to get rid of or reduce global warming technically rather than by reducing emissions. But I think it's actually wrong. I think it's the opposite, because the idea that removing CO2 from the atmosphere gives us an excuse to go on a wild binge of emitting carbon dioxide from fossil fuels, even if it's not true, because we don't need an excuse to go on a wild binge of emitting carbon dioxide. That's what we're doing now. And there's no reason, given the stupidity of the human race, there's no reason that the human race, when they were told, if they're told that you have to reduce your emissions or else, that they'll actually reduce their emissions. They won't. They'll keep on with the present status of letting other people reduce their emissions as long as I don't have to reduce mine. And that is going to lead us into disaster. So we ought to be finding a way to get rid of the CO2 and allow for humans to be stupid, not try to force them to be not stupid when you can't do that because of the innate stupidity of the human race. So CO2 removal, I think, is the answer, and it's not going to have the effect of allowing humans to behave in a different way, because they'll keep behaving in the same way anyway.
Yes, sadly, you're probably right. Trying to keep probably about 10 minutes more of questions, so I'll try and get through as many as I can and see if we can answer each one of them fairly quickly. So Will Saunders asks a question I might not want to know the answer to. Is there any hope to halt or reverse this ice melt?
Well, that was the question I was trying to get on to at the end, and to say we haven't got a good way to do it. If we're thinking about sea ice melt and because of all these other things that sea ice disappearance does that I talked about as well, the albedo change and the warming of the atmosphere to give you more sea level rise, that all of those things can be solved if we can bring back sea ice. But firstly, you can't really do that without cooling the climate in general. So that means basically CO2 removal. And otherwise, there isn't a good way. And the only way that's coming along potentially is this iron salt aerosol technique. But since no field research has yet been done on that, we have to kind of take it on faith that it will work, but hope we can do some research in the field, which is being done this year and next year.
Thank you. Right, Edred Whittingham asks, hi Peter, you've talked a lot about the need to remove CO2 from the atmosphere, even saying that this is our last option. You've also talked a lot about some of the companies working on this, Blue Planet, Climeworks, etc. However, what's the role for people without a science, technology, engineering, maths background in achieving this? I, for one, am studying politics and economics. Quick piece of career advice.
Oh, well, I would say if you're not a scientist or technologist, the best thing you could do is to be a concerned citizen. And so somebody who's involved with politics can be a concerned citizen. That there are organisations or the political parties even that are taking this very, very seriously and trying to get the world to change direction. I mean, the world has to change direction to solve this problem. So there are no limits to what you can achieve as a citizen, a concerned citizen, or a citizen involved in politics, to try to persuade your political representatives to do something positive. I mean, if you look at what Greta Thunberg has achieved, and there's one small person, and you can see what a lot of people can achieve if they all do this in a very serious way.
I'm so pleased you said that, Peter, and I'll just add to that a little bit, and seeing Belinda here on the chat as well. One of the things you can do, Edred, is go and join your parish council. Doesn't matter your age, so long as you're over 18, you can join the parish council. Many parish councils don't have enough councillors on it. Get them to declare a climate emergency by presenting the science to them, and then you can take action directly. You can also go and lobby your own district, county, and whatever levels of councillors as well. And instead of writing to your MP, go and see them, ask to see them and request to talk to them, but take action. Even go and stand in the county elections as an 18-year-old, I don't know what age you are, coming up next year, and stand with only one policy to reverse the climate crisis. And you'll have a lot of people to talk to and a platform to convince people. So, great. Right, from Matthew Hunter, Dr. Wadhams, Professor Wadhams, what is the time lag between the release of CO2 on the surface of the planet and the influence of that CO2 on warming?
Well, that's a good question. It's very short. So you mean CO2? CO2 is a bit longer. There's a lag. It takes a while for the CO2 to have an influence, and it's a number of years, in fact, to achieve the full impact of CO2 on climate. Methane is what I was thinking of, is much more rapid. That's virtually instantaneous. The methane release spreads around the planet in a few hours, in fact, a few days, and then immediately affects the climate everywhere. So methane is an instant climate change agent. CO2 is slower.
From Mark Oxley, what impact will this have on sea levels over the next 10 to 20 years?
Well, we've seen, I showed a graph of how the estimates of sea level rise have gone up and up, and they're still lagging behind reality. I think the IPCC's estimates were really pathetic. The two causes of sea level rise are warming of the oceans, which makes, when the oceans get warmer, they get less dense, so they stand higher, and release of water from melting ice sheets. And the release of water from ice sheets is now the major factor, Greenland and Antarctica coming along. And that, the estimates of warming, of the sea level rise by the end of the century are already well beyond a metre. The IPCC was estimating 20 centimetres, which I think was a criminal act of underestimating, because policymakers, people who have to build sea walls, act on the predictions they get from IPCC. If IPCC deliberately gives out a low value for political reasons, it means the world is left with sea walls that are not high enough. So that's an act that's, I think, the most criminal thing IPCC's done. But the estimates now done by glaciologists are measuring how fast Greenland is melting are getting up beyond a metre. And in fact, a good friend who died in an accident recently, that was Connie Stephan, who works on the Greenland ice sheet. His estimate was that it would be 4 metres of sea level rise by the end of the century. So that's pretty frightening as far as survivability of coastal cities is concerned.
Okay, thank you. Well, Saunders asks, is it true that companies are planning new shipping routes through the newly ice-free waters? And what do you think about that?
Yes, they are. In fact, there's somebody following me, I think, here who's going to talk a little bit about Arctic shipping. Yes, the Northern Sea Route is now routinely open for 3 or 4 months in the summer, and the Russians are using it very intensely. The Northwest Passage through the Canadian Arctic is not in use so much commercially, because it occasionally gets blocked. It's got narrow channels that can still get blocked with ice. So the Northern Sea Route really is on the way to becoming a standard sea route. Where you won't, in the summer months anyway, you would automatically sail between Asia and Europe, or west coast of North America and Europe by the Northern Sea Route. But Northwest Passage will take longer for the ice to disappear completely from all those narrow channels.
Thank you. I think we already know your answer to this, but we'll read the question anyway. Kevin Webb says, do you believe that scientists have been too conservative with their predictions? As in Southeast Asia, where I live, the weather has become unpredictable. The rainy season, you could have set your clock by, but not anymore.
Well, as I said, yes, I do think scientists have been too complacent, and the specific point that the question is making is, which is about the indeterminate nature of climate, is something that has just really been recognised now from study of extreme climate events. They're not called climate events even, they're called weather events, which means they haven't settled into a climatic system yet, they're just happening. And those are these either extreme hot or extreme cold events that happen through the year now in mid-latitudes. And it can be shown that that's actually related to the polar regions because of the decreasing temperature difference between the polar atmosphere and the tropical atmosphere, causing a reduction in the strength of the jet stream, and that's allowing air masses to mix in with one another and giving you weather events that are unpredictable and are very extreme as well, very extreme heat or extreme cold.
We've had another comment on the IPCC process and IPCC complacency, but I think you've covered that. Rodri Davis asks, what are the options, if any, to artificially stimulate ice creation or to increase its thickness?
Well, yes, personally, I'm pessimistic about the effectiveness of any methods that are being proposed to do that. But people are working on it, and there are serious efforts being made. The idea is you spray water over an existing ice flow to make it thicker, or you spray water into the air and it falls down as snow on the ice sheet. And the trouble is that all of these methods where you do something like that, you have to do it on a scale of millions of square kilometers to have an effect on the Arctic, which is 15 million square kilometers. So you can do it on an individual ice flow and you get an effect. But when you try to scale up, it's far too expensive and far too difficult and impossible to achieve the effect you want on the scale of the planet. There's a whole class of things that you'd like to do that you can do if you do them in your lab, or you can do them if you do them in a backyard. But if you try and do them on the scale of the planet, you can't do them. You have to kind of resist the temptation to go for these.
There was a question yesterday, actually, in one of the sessions where somebody was talking about methane being able to be used as a fuel, and in which case all this methane escaping is a great fuel source, and is there a way of capturing it? To which the speaker yesterday said, yes, but very difficult for the reasons you've just said across a vast scale of where the methane is coming out. But seeing the pictures today of the bubbles being caught under the ice, so effectively capturing them into a place, is there a method to collect up the bubbles under the ice and harvest the methane?
Well, a method has been proposed, and this was by, weirdly enough, by an oil company, Eni, the Italian oil company, and they said, well, why don't you do fracking in the offshore? So you have to have oil wells that are fracking wells in the shallow water, and you do the same thing. You create caverns and fill them with the methane and then pump out the methane. So you can, in fact, probably do that. The two problems are you'd have to dot the entire East Siberian shelf with oil wells, which will be, well, it can be done, but it'd be very expensive. And the other problem is that that's all Russian waters, and they probably wouldn't take kindly to anybody except a Russian oil company doing that. In fact, they wouldn't even want a Russian oil company to do it, probably. But in principle, you can do that. You can get rid of the methane by fracking, and hopefully you can flare it. People always complain about how wasteful it is to see oil flares in offshore oil fields, but actually flaring methane is a good way to get rid of its greenhouse effect, because it's 23 times as powerful per molecule as carbon dioxide. So if you burn methane and turn it into carbon dioxide, you're getting rid of most of its greenhouse effect. So my view would be, if we can't use it fruitfully as a fuel, then it's better to flare it than to let it escape into the atmosphere.
Right. We're very near the end now, so I'm going to do one more question, and while you're answering it very quickly, I'm going to see if there's one of the rest that are worth having a quick go at. So Brian McGavin has asked, are you saying methane is also being released from non-Arctic areas? You mentioned Bavaria. Before you answer that, Tony Goodchild has said a lot coming from North Africa too.
Oh yeah, huge amounts. In fact, I recommend a very good film in which I played a small role called Ice on Fire, made by Leonardo DiCaprio. It's a full-length film dealing with climate change. It deals a lot with methane emissions from both from the Arctic and from elsewhere, and it's showing that the largest individual sources of man-induced methane, there's natural sources like digestive systems of cows and so on, all those famous things, but the human-induced sources, which largely are leaks from pipelines and equipment, the biggest ones are actually in the Midwest of the United States, and they've got a really frightening film of some machine that's pumping up methane, and it's leaking everywhere, and measurements of the amount of methane coming from that single machine are that it's more methane than is coming from the whole of the Arctic, is coming from that one kind of klutzy ancient machine with lots of leaking parts. So we can do a much better job than we are doing, and the places where we need to do it are everywhere that methane is being pumped, which means pretty nearly everywhere in the world.
Right. And then a very, very, maybe not a single word, but a single sentence answer to Margaret Beasley. What does Peter think the chances are of getting substantial investment into marine cloud brightening through the private sector?
Well, I think it's good. In fact, the private sector is doing a couple of things at the moment. One is some work in Australia to try and cool off the area over the Great Barrier Reef and reduce the bleaching. And then there's an effort being made in the US to develop a marine cloud brightening technique. So Britain was way ahead of everybody else and still is just about, but it is being done elsewhere and largely by foundations and by private sector funding.
Great, thank you very much. I think we'll leave it there on the questions, as we're already more than half an hour over time. So absolutely fantastic, Peter, that's great. Just to finish off with a few additional comments and things, and a slight apology to anybody here who's not British and doesn't realise that today, the 5th of November, is a particular day in the British calendar, because this might take a little bit of explaining, but anyway, remember the 5th of November, the gunpowder treason and plot. I see no reason why gunpowder treason should ever be forgot. Well, on exactly a year ago, President Trump, hopefully then President Trump, rolled out a barrel of gunpowder under the Paris Accord and took America out of the Paris Accord, which was official yesterday. Well, on the same day as President Trump took them out of the Paris Accord, the world scientists issued their third paper. So the world scientists warning of a climate emergency, which is the 1-year anniversary today. So, and we're doing Peter's speech, who's been involved with the World Scientists Outreach Programme for several years now on that particular day. And to quote again from the World Scientists warning of a climate emergency, they say right at the beginning, scientists have a moral obligation to clearly warn humanity of any catastrophic threat and to tell it like it is. On the basis of this obligation and the graphical indicators presented in this report, we declare, with more than 11,000 scientist signatories from around the world, clearly and unequivocally, that planet Earth is facing a climate emergency. It's not by chance that the world scientists issued that on the day that Trump tried to take America out of the Paris Accord. We all hope that, I'm sure everybody here does, hope that Biden will get in and take America back in. But the world scientists and the warnings now signed by more than 15,000 scientists saying there is a climate emergency and we should take it very seriously. And in fact, the first sentence may actually be pertinent to Peter's comments on the IPCC, saying that scientists have a moral obligation to clearly warn humanity of any catastrophic threat and tell it like it is. So thanking Peter again, I'd like to do a little bit of extra housekeeping and things before we move on. We have to thank Pucker Herbs, who have declared a climate emergency themselves and are a B Corp, and Sebastian Pohl did a talk for us at the beginning of the week on food, and Pucker Herbs have sponsored this event. And then we have a whole stack